So before we get too far, I first want to see, is there anybody that's going to admit to not knowing anything about Spark? This is going to be a good news, bad news kind of thing. Bad news is that I'm not going to be able to spend a lot of time explaining really what Spark is all about, because I really want to talk about some of the pieces that start to go beyond Spark. The good news is I've got a larger audience for my book now. So we will start with a quick review of where the whole Spark ecosystem is to date. And you can start off by thinking of Spark as similar to Hadoop. And actually, after Alex's talk, you can actually think of it even more accurately as being similar to Scooby, in that it's a data analysis, big data analysis framework that runs across a cluster for you. And it has a Scala API to it, and actually the Scala API for Spark is almost identical to what the Scooby API is. I mean, you can literally change a D-list to an RDD here and there, a couple other keywords change, and you can pretty much run the exact same MapReduce job that you would run in Scooby over onto Spark. Spark actually lets you do some things you can't do with Scooby, so we can actually go further and run more generalized DAGs, and actually we'll disagree with Alex a little bit later about the viability of running machine learning jobs and such, because right, so we get to more generalized graphs of MapReduce operations, because one of the problems that Alex talked to you a bit about was that with Hadoop being very much based on HDFS, on reading things off from disk, running one pass through your MapReduce operation, writing the results back out into disk, that really limits you when you try and do interactive or iterative kind of algorithms. But one of the big differences with Spark is that instead of keeping your working data set back and forth off from disk, we actually store it in the RAM, the aggregate RAM across the cluster, which means that once you've got your data set resident in RAM there, you can actually iterate through it multiple times, or you can run an interactive query against it and not have to spend the time waiting for it to read off of disk all the time. So what that amounts to is that we end up with much lower latency on these jobs. To do, I mean, this is 100 milliseconds is basically for a null job, a job that does nothing. You're going to get a response back in 100 milliseconds, which doesn't sound all that great, except when you look at doing the equivalent in Hadoop, it would take you probably on the order of at least 30 seconds just to spin up the JVMs across the cluster, and still you're doing nothing. So you start to look at interactive kind of jobs, something more like a traditional database query where you want to issue an interactive query at a console and get a response back. You really want to see something that's kind of sub-second or at worst a couple of seconds response time, and you're just not going to get that with a Hadoop-based cluster, whereas we can do that over with Spark. And like I said before, we can actually start to run more iterative kinds of jobs as well and start to get into machine learning. So Spark was kind of the first step along the path. All these things are getting developed at the AMPLab over at Berkeley. It's a group of graduate students and faculty over there. It's actually starting to expand as well. But so Spark was, well, actually more like the second major piece that came out of there. The earlier piece was something called Mesos, which we'll see in just a little bit. But after Spark, we get to Shark, which, if you think of Spark as being similar to Hadoop, Shark is similar to Hive. And what Hive and Shark let you do is essentially issue SQL queries against your Hadoop cluster or against your Spark cluster. So that opens up a whole, it opens up being able to write jobs against your cluster to people that only know SQL, or even equally important, there's whole sets of tools and applications out there that know how to read and write SQL, and they can actually interact with your Spark cluster as well through Shark. Shark borrows directly from the Hive libraries. We take over the Hive metadata store, the actual Hive QL query language, which is, like I said, it's a subset of SQL. Then we also use the Hive parser and use the Hive libraries to generate the logical plan. But when it actually gets submitted to the Spark cluster, now we're running a Spark physical plant instead of the Hadoop physical plant, so that we start to get the same kinds of speed ups, because again, we're using in-memory sharing of this data set. So what you end up doing is issuing your Shark query, generating a result set from that. That result set you cache across the memory of the entire cluster, and then you can run further interactive queries or more quick Shark queries against it. Also, when we bring the stuff over into the memory of the cluster, we also can convert it over to a columnar store format, which then allows for a lot of compression and other speed ups as well. And again, so that maintains the low latency. Then the next step beyond Shark was something called Spark Streaming, which you can think of it as being somewhat similar to Storm Trident, where we're taking sliding windows over real-time streaming events. So you group up these events that are streaming into your system, and you end up essentially running lots of small Spark batch jobs against those windows of events. And if you can process those quickly enough, which of course you couldn't do if you were doing it in a Hadoop-based system, but we can do with Spark, then you can keep up with your stream of events and actually do real-time streaming processing across your whole entire cluster. So this is what the Berkeley Data Analytics stack ends up looking like. If you look at the stuff in white, that's all the existing open source stuff. I mean, you got your HDFS file system from Hadoop, you got Hadoop itself, Hive, Pig, then there's other things that can use the HDFS, things like Storm and MPI kinds of processing. Those kinds of things can stay within the Berkeley Data Analytics stack because, I mean, HDFS kind of ends up being the common denominator beneath all of these. The bottom level there, Mesos, that's a resource management framework. If you're familiar with Yarn out of Cloudera, that's something similar. If you want to run, so like if you wanted to run MPI jobs or a Storm cluster or a Hadoop cluster and a Spark cluster at the same time, or multiple Hadoop clusters or multiple Spark clusters, that gets to be pretty much impossible unless you've got some sort of resource manager underneath allowing you to share different resources, CPU and memory and such across the clusters. That's what Mesos allows you to do. And like I say, that was kind of the first piece that came out of the AMPLab, and it's since been picked up by Twitter and some others. So actually, most of the further development work isn't really done at Berkeley anymore on Mesos. So we've already talked about the Spark and Shark and Spark streaming pieces. And so 4 of the 5 pieces that I'm going to be talking about tonight are then Tachyon, which was just released a couple of weeks ago. And then the next things that will probably, I mean, let's say it's the most likely future for the whole Spark ecosystem because these next pieces aren't released yet. They may change some before they actually do get released. Some of them are still kind of more research projects. So this is kind of the way things look now, and there were things worth thinking about and learning something about, but they may end up, I'm not going to get into like trying to show you code or anything from these. It's going to be kind of a high-level motivational kind of discussion of these kinds of things. Yeah.
Which parts of this stack does your book cover?
Well, that's a good question, because the question is, which parts will the book cover? And Spark and Shark and streaming will definitely be there. Tachyon is an important enough piece that there'll probably be parts of it that are in there, but Tachyon is also very new, so there won't be an awful lot about it there. GraphX may get mentioned some, and MLBase and BlinkDB are probably far enough in the future that they won't make it into this edition. So the first thing we need to talk about is Tachyon, which gives us reliable file sharing at memory speed across the cluster frameworks. And okay, yeah, like I said, there was a recent Spark user group meetup on this, and thanks to Stoney, the video for that is available, and that's really where you want to go if you want to try and find out more about what Tachyon is all about, because like I say, I'll be able to go through kind of the high-level motivational points about Tachyon, but I won't really be going into the details of it. And okay, if we want to continue to do our comparisons here, you can think of it as similar to HDFS. It's a distributed file system that's easily used from MapReduce jobs, Hadoop jobs, or from Spark. In fact, the Spark and Shark API for reading and writing to Tachyon is essentially identical to what it is to write into HDFS. So you can literally write a job now that's going to read and write from HDFS, change just a couple of lines, and you're going to be reading and writing from Tachyon. Now, why would you want to be doing that? And what it mostly comes down to is that you want to be able to share data sets among Spark and Shark jobs. Right. So if we we look here, we see Tachyon is essentially working as a caching layer on top of some sort of existing underlying file system. And in most cases, that's going to be HDFS. And so then you'll be reading and writing to Tachyon, and more than one Spark or MapReduce program can then see the same data set within Tachyon. You'd be able to do the same thing with HDFS. I mean, if you thought about running one Hadoop job, take the results of that, write it out to HDFS, then another job could pick up that result set and start working further with it. That kind of thing was difficult to do before we had Tachyon in Spark or Shark. Actually stealing a set of slides here from Ronald, the key developer on Shark, and these all mention Shark, but they pretty much apply to Spark as well. Because this is a situation we have just running one Shark job against the cluster. You end up taking blocks of data off from your HDFS file system, reading them into the memory of the Shark system, and then you can run a set of interactive jobs across that. But that's really limited to this one Shark context that has access to that memory. Your problem then is if you have more than one user or you have more than one job that wants to access this same set of data that's now resident in memory, it's not really a good way to do that. What you end up having to do is there's actually something called the Shark server, which essentially adds a server layer on top of this, that instead of one user or one job directly interacting with a Shark context, it goes through a server layer that's going to then aggregate multiple jobs and share this one Shark context. And I think I skipped this slide. Oh, okay. That's fine as far as it goes, but you've actually, there's too tight a coupling between the actual, the job that's, between the execution part of the job and the storage layer part of the job. Because what ends up happening is that then if that Shark server ends up crashing on you, well, it usually doesn't end up stopping there. What happens next is that you'll lose the entire storage layer as well. So now you've aggregated multiple jobs into this one Shark context, and now everybody's job is dead. And it's not only that, there's not really a good way to recover it. You've got to go all the way back to HDFS and restart that. And you can try and compensate for that some by running multiple Spark or Shark contexts. But now the problem is that we end up, if we want to protect against losing a set of data, we end up having to duplicate it across multiple Spark or Shark contexts. And so we're duplicating the amount of memory that we're using across the cluster. And what we really want is to add a separate layer in there to kind of separate out the execution from the storage layer. Because what ends up happening now is that what's going on here? Hello? Something not working correctly here. But what we're supposed to be showing is that if, say, this cluster crashes with a Tachyon system, the other guy will still be able to access the data sets that are still be resident in Tachyon. The Tachyon won't crash just because the execution engine crashed. And because of some of the details of the way Tachyon is implemented that I won't be able to go into, it actually stores a lineage of how a data set was how a data set was constructed. And so if we do end up losing a piece out of Tachyon data that was stored on one of the nodes in the cluster, if that node goes down, we're actually able to work quickly recover that. And so we do get instantaneous recovery within Tachyon. Current release, yeah, it's a developer release, so it's not really production ready yet. And we do RDDs are kind of equivalent to these D lists that Alex talked about before. It's kind of the fundamental abstraction of what a piece of data is. RDD is a resilient distributed data set, so these are these distributed collections across the cluster memory. And so support for those, sharing and caching, those is in the current developer release. There's an HDFS API to it, so you can actually write Hadoop MapReduce jobs using Tachyon. But things like being able to directly put these column-oriented storage that I talked about from Shark before, you can't. Eventually, we'll be able to take those and write those directly into Tachyon as well. So if you thought about it before, you would read your Shark data off from HDFS, and change it over to columnar storage in RAM, and then have to write it back out to the non-columnar storage format back in HDFS. Eventually with Tachyon, you'll be able to take that converted columnar store and put it directly as a raw table into Tachyon, and then not pay that kind of reorganization cost multiple times. And then the next release will also introduce fault tolerance for, there is a master node in Tachyon currently that's kind of similar to the Hadoop name node, and that's a single point of failure right now. And we'll be taking care of that in the next release. And there actually is potential for further releases to start to support that kind of directly writing mutable changes to your data set within Tachyon itself. So those are all things that will be coming down the road, but aren't really there yet. So GraphX, okay, we're back to our diagram here. So GraphX is something that's built on top of Spark, but we're looking at graph processing now. Yeah, so there's a kind of, I'm trying not to talk too much about GraphX tonight because the Berkeley guys haven't really talked about it yet. There's really just kind of one paper out there now on it. And this is a very nice short paper. It's like a 6-page paper. If you take a look at it, you can learn an awful lot more about how it's actually implemented. So I'm just going to give you the high level again on what this is all about. So graph data structures and algorithms are quite important now. If you want to look at the data, I'm sure a lot of you are familiar with like social network graphs and stuff that are out there now. And that's kind of a familiar one to a lot of us, but there are a lot of other kind of data sets out there that are kind of fundamentally graph-oriented in nature. And then there's certain algorithms that are most easily expressed as graph algorithms as well, about nodes communicating messages to other nodes. So if you look at a page rank algorithm, it's all about, well, in the context of websites, it's about which websites are connected to other websites. And so there's a natural graph kind of orientation there. And so if you actually try and write PageRank in Hadoop with its data parallelism orientation, it's kind of difficult to do it. And you'd much rather have a set of graph primitives that allow you to say, these are nodes, these are edges between the nodes, these are messages that are getting passed, this is what you do when you get a message, and that sort of thing. And so that's what GraphX and other graph processing frameworks start to allow you to do. So the aim of graph parallelism is to reduce the communication and computation by exploiting the graph structure itself. So like I said, if you try to write these algorithms using kind of the normal Hadoop primitives, you end up doing a lot of extra computation and communication across all these nodes, because Hadoop fundamentally wants to scan through the entire set of data and do something to it instead of being able to work with a reduced set. Okay. So yeah, the first problem we have in trying to do any kind of graph processing is that the data that we get typically needs to be munged or mangled into some sort of graph appropriate format. I mean, data sets you get out there aren't already set up to be used directly, and they're not expressed as nodes and edges. You have to kind of manipulate the existing data in order to turn it into a usable graph. And then once you've actually got them expressed as a graph, your graph algorithms, like I've said before, don't typically want to run efficiently, and they're not easily expressed in a framework like MapReduce. So the solutions to these are you need to do you typically end up needing to do your data munging or data wrangling with a separate tool from your actual graph processing framework. So oftentimes, actually, MapReduce or similarly oriented frameworks can actually do that quite well. So there may be, so there are existing graph parallel tools and frameworks out there. Things like, right. So these are all working with passing messages between graph nodes. And so there are things out there like Pragle, which is a batch synchronous parallel processing, what it amounts to. So these work kind of as synchronous super steps. So you may have this whole set of nodes and connections, and they know the messages they want to send. And so they get stepped through in a synchronous fashion that all the nodes are going to generate a message. All of them are going to send to the next nodes in this step of this super step. And then we're all going to coordinate and generate the next message. We're going to run the next super step. And so they continue to process in this kind of synchronous fashion. And then there are other things out there like GraphLab and its power graph set of algorithms that actually can work asynchronously, which can actually end up providing you a lot better speed up. But in both of these cases, like I said before, you typically end up needing to do a data wrangling step before that. So you end up kind of in a two-phase kind of operation, where first we're going to manipulate whatever raw format of the data we got into a graph format, and then we're going to run these graph processing tools against it. So GraphX replaces the earlier Bagel library, which used to be, well, it still actually is in the Spark code. And Bagel is kind of an implementation of Pragle, but using Spark instead of Hadoop. But GraphX does to borrow ideas from GraphLab, one of which is vertex cut algorithms, and some of these details, like I said, you can find in that paper I referenced earlier. And it's tightly integrated with Spark. So, yeah, so by adding a new data abstraction called a resilient distributed graph, again, those details are in the paper, and we're not going to get into them too much tonight. And yeah, it's getting kind of interesting that these new frameworks get implemented on top of Spark and get implemented in an astonishingly small amount of code. I kind of expect that Reynolds will be presenting on GraphX in the not too distant future, and he'll get into a lot of these details that are also in that paper. And you'll find that the framework itself is a small amount of code, and then actual jobs expressed using the framework are very tiny amounts of code. I mean, the entire PageRank algorithm can be implemented in just a handful of lines of code. Okay, so then when we look at performance of GraphX, so I talked before about Pragle, which is kind of this Hadoop-oriented batch synchronous processing kind of way of doing things. And then there's also GraphLab, which is asynchronous way of doing things. And so if you implement the same PageRank algorithm on both of those, you'll find that GraphX runs roughly an order of magnitude faster than Pragle does, but it runs an order of magnitude slower than what GraphLab does. So it's kind of fitting in between. What that amounts to in a practical sense is that the GraphX will probably never be equal in performance to the specialized tools that are out there, like GraphLab. But it's because of the nature of Spark and its low latency, we'll actually be able to interactively or iteratively change the graph structure that we're working with, which is something that you can't do in that two-phase process I was talking about before, because your data wrangling or data munging step using Hadoop or MapReduce, that's going to take you, it's an all-day batch kind of job, similar to what Alice was talking about before. Whereas if we can keep that all within those two steps, all both within the same Berkeley data analytics stack, then we can do interactive or updates of the actual graph itself. So even though the final graph processing algorithms may not run as quickly as what a more specialized tool like GraphLab can do it with, there may be enough advantages that this kind of intermediate performance will still be an overall win in the end. Okay, so let's move on to the next piece, and this is MLBase. So again, we're back to another piece that's built on top of Spark. And yeah, there'll be the San Francisco Bay Area Machine Learning Meetup is a week from tonight, and that's where they'll actually be presenting on MLBase for the first time. And where is it? Yelp, I think. Yeah. And I checked a couple of hours ago, and there's still a few slots available there. So if you get enough interest in, so I'm actually going to try and do this all with a single slide here. So what we need to do first is kind of ignore the ML machine learning kind of tags that are applied to this, and think of this as just a typical relational database kind of model. So in your normal RDB mass, you come in with your end user is kind of this guy in orange up the top, and he doesn't really know all the details of how a relational database is implemented. Doesn't know really anything much about hash joins or loop joins, or all the different possibilities of how things are actually implemented within the database. What he's giving you is an SQL query, which is a pretty high-level description of what the kind of results he wants, not how the job is actually done. And the system will take that and parse it, run a query planner against it, run an optimizer against it, generate some sort of physical plan against that, and then that will eventually get run against the database. And your smart guy over there, he's the one that ends up having to write all those low-level database details about how things actually get implemented and how the optimizer itself runs and that sort of thing. So what MLBase is attempting to do is a similar sort of model, but instead of issuing SQL queries against a database, what we want to be able to do is issue machine learning-based queries. So you may say, instead of select these rows from a database, you may end up saying, against this database, I want you to cluster it for me. And so then that high-level description of what you want will get passed into a query planner and optimizer, similar to what the SQL way of doing things is. And that will turn into a set of runtime jobs against a Spark cluster, which will, yeah, again, I don't want to go too much into the details because these are, we'll be stepping on the toes of the guys presenting in a week here. But that should be, I hope, sufficient to get you interested in the idea of being able to, I mean, one of the big problems we face within machine learning or data analysis right now is that there's just not enough of these smart guys that know how to actually run all the tools at the level of detail that the frameworks require. So if you have a system like this that allows you to express a query at a much higher level and be able to handle the creation of the plans, the running of those, the evaluating of the results of those, and presenting those all at a higher level to the end user is something that's very valuable. That actually, this diagram shows, I mean, that kind of high-level stuff will only be in phase 2 of MLBase. The first phase of it will be really implementing kind of more of the low-level libraries. Yeah, it's Tony.
So is this going to be used to train and cross-validate and check for like overfitting automatically, or?
Yeah, so those kind of things. I mean, exactly how all the details of this are going to work out is still yet to be seen. But yeah, so when you ask for something to be clustered, the plan that it can end up generating may end up, I mean, when you've asked for clustering, you haven't told it which clustering algorithm to use. Yeah.
So it's going to do unsupervised as well as supervised?
I can't really speak to the details too much, but I mean, my understanding is that would be part of, I mean, both,
So
yeah.
it's going to work with non-labeled, non-tagged, non-labeled data. Those, like the supervised means your data is already labeled.
Right.
And here you're like looking at non-labeled data.
Yeah, again, these are probably questions that are better reserved for the guys next week, but the overall idea is that you'll be able to express your desire at a high level that will actually end up, can be implemented as a plan that's going to execute potentially multiple clustering algorithms or multiple other machine learning algorithms, and then be able to present to you some results of those that are expressing how well each of the different clustering algorithms worked. And
Is there a paper on this, or?
there's at least one paper out there, I believe.
Who's working on this?
I'd have to look up the details of exactly who's working on it for you. It's up there. I believe there's.
Anything about like sparse autoencoders, like the semi-supervised learning of unlabeled data?
From which?
Like there's different methods of looking at like non-labeled data. If there's a paper, I could probably go over and see it.
Yeah, I don't know if there's a paper specific to what you're asking about, but I think there is at least one paper out there on MLBase. There should be I believe there's an MLBase web page that's accessible off from the main AMPLab page as well.
I found the paper for GraphX, like I found I started reading that one. But
Yeah, sometimes these papers are a little bit tricky to find, but I'm sure that the guys next week will be giving you an awful lot more pointers as to what's out there. Yeah, and yeah, some of this stuff was actually introduced at an AMPLab retreat just over this past couple of days, and not all those details have been publicly released either. But anyway, you should, hopefully at least from this, you can get the basic idea of being able to express machine learning queries in kind of the same fashion as what you express SQL queries. And so these low-level libraries that will be in the first phase of development, those actually end up being conceptually somewhat similar to like Mahout or other machine learning libraries that are out there that are Hadoop specific, but these will be Spark specific and then able to be optimized for the way Spark can handle things in memory and such. So now we're starting to get off kind of really into the research fringe with something called BlinkDB. And this is all relies heavily upon using approximate answers to your queries, which becomes important. Like I say, yeah, it's a research effort now. You're not going to see a lot in the way of really anywhere close to production-ready code for a while. And this post of Jan Stoico up at the AMPLab covers pretty much what I'm covering tonight, but in more detail. It's kind of it's a good motivational paper, but we're still not seeing anything in the way of details about how things are actually implemented. So the problem that we're facing right now is that the rate of growth in the available computational resources is pretty well understood. I mean, that's going by Moore's law, essentially. You have a pretty good idea of how much more computing power you're going to have 2 years from now versus right now. But we're also starting to see that the rate of growth of data is actually exceeding Moore's law. And I mean, at first you'd think that, well, we're doomed. I mean, we're just going to get overwhelmed by the amount of data that's out there. There's no way we're going to be able to keep up with it. But if you start to look at the key insight to this problem, is that right now we're generally computing exact answers to things. We go through all of our entire data set and run clustering against it or something, or do some sort of machine learning algorithm against the entire data set. And that gets us as good an answer as we could possibly get, but I put the exact in quotes because it's still really not a perfect answer, because our data sets aren't perfect. There's a certain amount of error present in the data. So what's the point of computing this exact answer when statistically there's still going to be error present in whatever you compute? And so most of the time, approximate answers are good enough. If we can define to know that we're going to have our error bounded by a certain amount, it's usually actually, maybe that's what we got with our exact answer before. We're kind of hiding the fact that there was error involved. And to create approximate answers, you don't need to be looking at the entire data set. You're going to be looking at just a sample. And what's really important is that the growth in the sample size is needed to maintain a certain error bound actually occurs much slower than what Moore's law does. So if you get twice as much data 2 years from now, the size of the sample that you will need to create the same error that you did before will not be twice as great. And so Moore's law can actually more than keep up with the rate of sample size growth, even given the higher rate of overall data growth that we're seeing. So what actually ends up happening is that we're not doomed, we're actually better than saved. Because Moore's law is increasing faster than what the required sample size is, we can actually improve the accuracy of our results over time. That's one option, and that's kind of what this graph at the bottom is showing you. Moore's law is going in the gray there, which is probably hard to see. Data is going up with the green line, but the actual size of your error is actually decreasing over time. The other option you could take is to get the same level of accuracy, just faster. Or you can start to run additional tests, additional queries against the same data. And so that will hopefully give you much richer insights. So the whole point of all this is that if you can architect your system to be using samples and approximate answers, actually your future is looking pretty good, even though the amount of data is increasing at this seemingly insurmountable rate. I mean, it's really not a problem as long as you can handle approximate answers and samples. So when we're going back to this to look at BlinkDB is now implemented kind of above Shark and Hive. So the idea is that it's going to be another SQL kind of based query. So you're going to have SQL queries that will then be expressed with an error bound and a time in which you want to get an approximate answer back. And like I say, that's just one kind of research effort that's out there, but it's worth really keeping an eye on. I mean, this is a pretty key idea going forward. So it's not just BlinkDB that you need to be looking at, but how other systems are going to be answering this approximation and sample size kind of problem in the future. So now we're actually up to, those are the 4 pieces that are coming out of the AMPLab. And now we're actually going off into the piece that I'm more directly involved with, so that's outside of the AMPLab. And the problem we're facing right now is that we need to be able to improve the code base that's out there, but we're starting to step on each other's toes and trying to do so. So Spark and related code, I mean, things like Shark and Spark Streaming and Tachyon, it's, like I've said before, it's actually a surprisingly small code base. So that means it's pretty easy to understand it, comprehend it, and the development community around it is pretty open and friendly. So it's pretty easy to get started using it. And there actually are a quickly growing number of contributors to the code base. But the smallness of the code is actually a problem for us as well, because everybody's crammed into this one small piece of code. And so we're starting to bump into each other more and more. And so who's this we that we're talking about that are running into these problems? Well, a couple of years ago, it was just grad students and faculty over at the AMPLab. But that's starting to expand now, that the AMPLab itself has hired on a group of staff developers. They're headed up by a guy named Matt Massey. So if you're an industry developer wanting to use the Berkeley Data Analytics stack, Matt's a good guy to know. And his group is kind of tasked with turning this AMPLab code into production-ready distribution. So being able to easily deploy the code, make sure it runs 24/7, all those kinds of good things that aren't typically associated with research projects out of academics. But the AMPLab is starting to try and push it more in that direction. And then that group is also has the task of maintaining developer relations with outside developers. Then there's also academics outside of the AMPLab. There's some of them, other groups at Berkeley that are using it. And there's actually been a few papers that have been contributed. I can't remember where the guys are from, but there's a very interesting paper out there on Sparkler that was contributed from a group outside of Berkeley. And Matej Zaharia himself, who was the lead developer on Spark, he's finishing up his PhD in the next month, basically, and hasn't announced yet precisely where he's going, but he's sticking in academics, so he'll be another academic that's outside Berkeley. So those folks need to be coordinated more into the development effort. And then there's a whole set of industry developers like myself who are contributing code directly back into these open source projects. So this we is now starting to get organized, and we need some sort of roadmap to enumerate and prioritize all of our development efforts. And we've started to recently see more communication of what the AMPLab's roadmap is. If you look at that video of the Tachyon meetup, Ronald actually went through and gave you a pretty good idea of what's coming next in coordinated Shark and Spark and Tachyon development. So we're starting to get more information directly from the AMPLab on that. And that's really not sufficient because we are starting to get more and more people contributing code from outside the AMPLab to the point where there actually are more non-AMPLab developers contributing code to Spark and related projects than what there are actual developers at the AMPLab. And yeah, the needs of us outside developers, our needs and priorities, they're not always the same as what the AMPLabs are. Now, it's been pretty good so far. We haven't found any real conflicts, but we still need to have some way of being able to express and coordinate the needs of industry as distinct from the AMPLab. So what we need is a wider roadmap, something wider than just the AMPLab's ideas of what should take place next. That's going to include all these community efforts and contributions. So that's actually something that I've been involved with over the past couple of months is organizing and coordinating kind of a steering group. Now, that's in quotes because we haven't really decided exactly what to call ourselves yet, but it gives you an idea. We're trying to present some sort of coordinated roadmap. So the steering group is kind of composed of, well, it's people from the AMPLab, but it's also a collection of industry developers from companies that have been contributing heavily to the Spark and Shark code. So we first met up almost a month ago now to try and put together, our first job was to try and put together this kind of community roadmap. So these are some selected items off from that roadmap, things that we added kind of to the AMPLab's list of things that we want to see next. One of which is job progress indication. Right now, if you kick off a job into your Spark cluster, you basically get no feedback as to how far the job is progressing. You don't really know whether it's crashed or whether it's making good progress or just what's going on. Another piece that we want to see soon is more general cluster monitoring about the health of your entire cluster, which nodes are up, which nodes are down, how much of their CPU is being used, and all that sort of thing. Getting to, I mean, I was kind of envying Alex when he was talking about being able to, with just a couple of lines, being able to deploy a new Hadoop installation for them. We'd like to be able to get the same sorts of things working within Spark and Shark and related stuff. And to do that, we are looking at using Chef or Puppet scripts, making those available. Yes, Tony?
Is anybody working on that yet? Or?
So the first phase of this was just kind of all of us agreeing on which things need to be done and which kind of the somewhat a rough idea of the priority of them. And then so we're kind of working next, well, not quite working on it yet, but the next step will be figuring out who is going to be working on each one of these different jobs. So it's more just at the stage of what jobs need to be done at the moment, and the next step will be who's going to be actually doing them. Some of them, people have started to do pieces of them, but like I say, the problem of us stepping on each other's toes is present. That there can actually be multiple groups starting to work on the same piece, and now we've got to kind of back up a little bit and re-coordinate those. Yeah, another possibility is to work on it's possible to run Spark as a standalone cluster now. So it doesn't use that Mesos or other kind of resource sharing framework underneath. It just takes over the entire cluster, which is really nice in kind of development or testing kind of modes where you're not really worried about sharing an entire cluster in production use. You just want to be able to implement something fairly small against maybe even against virtual machines on a single laptop or something like that, or against a small test cluster. But there are actually, in certain situations, I mean, if you want to run in production and you don't have any need to run another Hadoop or MPI job or some of these other things, if it's perfectly fine with you taking over the entire cluster, there's really no reason why you shouldn't be able to use this Spark standalone cluster in your production environment as well. The problem is that that's not really a high availability environment right now. If you lose a master node, you've lost the entire cluster. So one of the guys that's in part of this steering group has actually done a fair amount of work already with Akka clustering. And so he's looking at starting to implement high availability within the Spark standalone cluster mode. Then, yeah, how your data set gets partitioned across your cluster is, there's room for improvement there. And yeah, there's other things coming as well. But this steering group is really not meant to exclude any of the rest of you. We think that a small group like this is useful in order to be able to conduct discussions where, I mean, we're intending to continue meeting kind of on a monthly basis and be able to make some rapid progress within a small group. But yeah, so the first step is if you actually have been contributing code or think you will be contributing code in the near future, and you think that you should be part of this group, well, go ahead and get in contact with me. I mean, we haven't formalized procedures for admitting people to the group, or even worse, kicking them out of the group. But so now actually is a pretty good time to try and get involved with it if you think that's where you want to be. But this small group is not meant to be some sort of secret society that's going to be making all the decisions for Spark and Shark, and we're going to say what's going to happen, and the rest of you just have to live with it. That's not at all what we have in mind. So your contributions are still prized, and we're going to be trying to make it easier for you to productively contribute to the code and still function in this coordinated manner so that your stuff doesn't get rejected because it's conflicting with somebody else's or whatever. So as part of that, the AMPLab is going to start to make much wider use of their Jira system, which up until now has been mostly just a bug reporting system. But we're also going to start to see more larger or design kind of oriented issues being posted to Jira and be discussions of them there. And yeah, so there's the URL for that. And like I say, we had this first meeting of this smaller group a month ago. We generated some raw documentation out of that we're supposed to have it available for you already by this point to kind of flesh out more some of those bullet points I gave you, some of our ideas of what need to be done, and then so get fuller descriptions of the problem sets we want to work on, get Jira issues for those opened, and be able to carry out more of the community discussion of those. We're not quite at that point yet, but the intent very much is for the results of these monthly small group discussions to, within a couple of weeks, be available to the wider community and get a larger discussion going as well. So, yeah, so all of that stuff will be coming out in a wiki that will be hosted over at the AMPLab as well. And I think that's about where we end up with, except of course that ClearStory is also hiring. So.